The motivation for this flyby topology was to improve the signal integrity, and as you can see here, the flyby topology does improve the signal integrity, and the data eye is much wider than on the right than is on the left picture. So when right leveling occurs, or this flyby topology is happening during a write cycle, the skew between the clock and strobes are increased due to this flyby topology. Now what we do is we do a write leveling whereby we remove these delays or compensate for these delays by changing the timing for each byte lane. Now this delay or skew that is introduced because of the flyby needs to be managed during the read and write. Here you see the read adjustments or the methods that we use to adjust during the read cycles. So as you can see, the commands would arrive to the first DRAMs, and then as they progress and propagate through this through the line, and they will reach to the last SDRAM, the command will arrive at each of these SDRAMs at a different timings, and they would issue their read, or they would send their information on the data bus at a different times. So what we do in our controller is we have a timer for each byte lane denoted by CPO value, whereby we'll tell the controller that when to expect each of these byte lanes to arrive, and hence we compensate for the skew that was introduced based on the flyby topology. During the write cycle, all the data would be sent. If all the data are sent at the same time, then the SDRAMs would not expect them at the same time because of the skews that are present in the command structure. So what happens here is during the initialization, the memory controller figures out what these delays are and would send each byte lanes at a different time with a needed delay to compensate for this flyby skews introduced. And all we need to do in memory controller is select the write leveling, and this process occurs automatically during initialization by the memory controller. So as you can see, both read and write are compensated for automatically, and a simple selection of this automatic adjustments would take care of the skews that are introduced by flyby topology. The DIM mirroring or mirror DIMs that you can buy are so when you purchase your purchase a DIM and it specifies in the datasheet that it's a mirror DIM, it indicates that there are two chip selects or two ranks available on that SDRAM, and the routing that is done between the two ranks are so that the stubs are reduced and the traces are reduced by switching some of the signals, so there's no cross connection required, and that would improve the signal integrity. So this is nothing that you need to do. It's just if you purchase a mirrored DIM, then you need to make sure that you have selected the mirror DIM register in the DDR to tell the controller, to tell the memory controller that the memory used it's mirrored, and the signals would automatically be switched to compensate for that adjustments that is done in the mirror DIM. So in this section, we're going to talk about the initialization and register configuration. The initialization flow for DDR2, as you can see here, is power up and wait for the DDR controller initialization. Once the stable clocks are available, wait 200 microseconds, and then set the map enable to enable the memory controller. Once memory controller is enabled, then it automatically does the following, which will precharge all command is sent, which would close any open row buffers. It would initialize the DRAMs, and after a certain amount of delay that is required in the SDRAMs, then it would be ready for operations. So basically, this timing diagram or this chart will show you the flow of operations, but there's nothing that you need to do after memory controller has enable bit has been set. In the DDR3, the flow is very similar. All you need to do is power up, set your registers in DDR, give it some time, and set the mem enable. And once that is done, then the rest happens automatically by memory controller. There are two types of memory registers when you're trying to set your DDR configuration. I would divide it into section that is provided by the SPD, is predefined in the data sheet and the DRAM data sheet, and those values are just making sure that you follow the parameters as indicated in the DRAM data sheet. Then the second portion, or this second group of registers that you could program, are non-SPD, whereby you are providing information to controller to tell it to manage certain aspects in a different ways. Here we have the on-die termination, we have driver impedance, we have the clock adjust, write data delay, or cast preamble override values, or the 2T, 3T timings, whereby you are sending the address and command in 2 clock cycles to increase your address and command I. Also the burst type selection or write leveling start values. So these are the list of the items that, examples of items that you need to set or select based on the activities that you want to do, or the selections that would best fit your application. So how do we adjust or optimize these timings? The parameters that are not part of the SPD. Here are the list of items that you need to pay attention to: clock adjust, write data delay, CPO, 2T, and write level enable, and the burst shop mode. So details of each of these would be that clock adjust is that you need to shift the clock so it is center aligned to the address and command bus. As we discussed earlier, SDRAMs are very simple devices, and we need to provide informations or the clock and the data, clock and the address and commands in a fashion where they just need to, as soon as they see the rising edge of the clock, they will sample the information for address and command lines. So usually, if the clock adjust is not set to, or is set to 0, or is not set to any value other than